Now here's the problem again. Here's the linear operator, and we want to figure out the function y that satisfies this differential equation, where this L is the operator associated with the typical linear differential equation, second order or third order. In an earlier video, we looked at the example where the right-hand side is simply the monomial, or sine or cosine, and e to the kx. And if it's a sum of this type, you can combine this one linearly, and we can answer lots of variations of the linear combination of these things. The next problem here we would like to consider is this Vx being product of these two these type. For example, xn multiplied to the trigonometry or exponential functions, or cosine or sine multiplied to e to the kx, or sine and cosine multiplied to itself, e to the kx multiplied to itself. If you think about how the sine times the cosine can be written as the sum of sine and cosine, it is not that interesting case. So it is really the interesting case is multiplying these things to itself, different type of multiplied to each other. So for example, x to the n times doesn't matter the sine or cosine, but of this type, this is the thing of the multiplied to cosine part, xn multiplied to the e to the kx part, or e to the kx. They usually write exponential first because it's how the polar form of a complex number is written. So these are the cases, I think. And this is a type of example that you remember from Calculus 2. We can recursively write down the integral formulas of this one, antiderivative of this one. I think it's similar to that. You have to just understand what happens to those, how this one goes down to the one level, and as we go through this operator. And all of this is can be solved the same method we've been doing this, judicious guessing, and think of especially when L is the linear operator, the linear operators with the constant coefficients. Since we'll be differentiating a product of two functions, let's think about how the product rule works when we have to differentiate more than two times or one times. So this is the product rule is usually introduced in the first course of calculus. Then if you want to differentiate it one more time, then you have to apply the product rule here and there. And this is what happens. So you differentiate the product of two functions two times, we'll be differentiating each of the product. If you differentiate this one using the product rule, sure we have second derivative show up and in here. But when we differentiate this one for one more time, and the second factor here, when we're applying the product rule to the first factor, we'll have f prime and g prime. When we apply the product rule here to this first factor here, then f prime and g prime. So these two together makes it 2 times f prime dot g prime. And if we differentiate the second factor here, we have f dot g second derivative. So this is what happened when you differentiate the 2 times. The product rule applied 2 times. This coefficient 1 in front of this part and 2 in front of f prime dot g prime, and this coefficient here is indeed the second row of the Pascal's triangle. And if you think about when we're doing one more time, which we might not do any of this example that involve the third derivative, but it is easy to state it here, and we'll do. If you apply the product rule in here, we'll pick up third derivative here and g. And when we differentiate second factor, and you can see when you differentiate this first factor one more time, they have exactly the same kind of order of derivative for each factors. Have the second derivative and first derivative. As we differentiate this part, you'll have second derivative and first derivative. So that's easy to see. These two add up to altogether the same term. That's exactly the principle of constructing one next row of the Pascal's triangle. All you have to now verify is that when you differentiate this part one more time, it agrees with differentiating this part one more time. So f prime, g double prime, f prime, g double prime. So again, we get the coefficient that appears in the Pascal's triangle, and everything here is differentiated except this last bit. So we have f g triple prime. So this binomial expansion is going on, not that f is raised to the third power, but differentiated 3 times. These are the Pascal's triangle. Since we'll be dealing with the example of first derivative and second derivative, this example will be useful and handy.